welcome guys. So this video, this is a new playlist called the series test. Also, in this playlist, we will talk about the common idea of how to determine a series, whether this series converge or not. Okay, so we will introduce like the limit test, and also a very famous like ratio test, or the integral test, and like square roots or other test. Okay, and we already proved some alternative test or something results, so I will compile it. So yeah, this is a new series, and we will talk about many examples. So this is the first video. Let's talk about the first theorem called the limit test. So this theorem is, I think, also common in the high school, but seldom people like to talk. Okay, so suppose S is a series from 1 to infinity. So idea is that if if this an converge, then limit n goes to infinity, an must be 0. So this is what we gonna to prove here. Okay, so this has an implication such that if limit n goes to infinity, an is non-zero, then sum of an diverge. Okay, so the first example is that this example is so famous that not so famous. It's a simple example. Suppose you do this, right? So this from 1 to infinity diverge, since that the limit n goes to infinity, n divided by n plus 1 is 1, right? So it's non-zero. Okay, and yeah, and the second example I want to talk is that the converse is not true. So second example, I think everybody knows about converse. So second example is that if you take this. So this is a famous harmonic series, and I will leave a video that you can use an elementary proof to prove it's asymptotic log n. So even though n goes to infinity, 1 divided by n is 0. Summation of 1 over n still diverge. Okay, so this means that this theorem can only go these directions. Okay, so now let's give it a proof. Okay, so let's go back to the. So we need to use a limit definition, right? Okay, so let's see. Let's define sk to be n from 1 to, or maybe they call it as n, k from 1 to n. AK. Okay, definition. So we know that from definition, suppose converge, right? It only means that Sn converge. So that means for all epsilon greater than 0, you can find n integer such that when n greater than n, then you must have your Sn minus the limit. Let's say the limit is s minus s is less than any epsilon, right? So I choose epsilon divided by 2. Okay, so that means there exists the integer n such that for every n greater than this n, then you always have this condition. So what, right? So your s plus 1 minus Sn will less or equal can be written as Sn plus 1 minus L plus. So let's do it slowly. So Sn plus 1 L minus Sn minus L. So that's or equal to Sn plus L plus Sn minus L. So since they are all greater, let's see, S, sorry, it's not L, I'm stupid. Okay, so since everything is less than epsilon divided by 2, right? So epsilon divided by 2, epsilon divided by 2, so this is epsilon, right? So so what is this, right? So what is this? This is an plus 1. Okay, so translate all the language. We know that for epsilon greater than 0, we have some integer n such that when n greater than n, then we must have an plus 1 less than epsilon, right? So however, since I only use n plus 1 and n, right? But if you use higher, you still prove it. You still have this result. So that means this statement is the same as. So translate the definition, just means this, right? And the absolute value is a continuous, so which tell you that this. Although this is just yeah. Okay, so yeah, this is the proof. So very easy. And the next time we will talk about more integral test proof, more series test proof. So what I want to mention is that in the advanced calculus that there are many things which you think is obvious, right? But actually it's not. Yeah. So that's it.